Now let us look at the two examples which we are going to apply for method of joints. Now compute the force. Let's look at the example 1. Compute the forces in members in each member of load L loaded cantilever by truss cantilever truss by the method of joints. You can see here this is a simple structure with triangles of equal distance. Each plane is of 5 meter, and then each plane is connected externally to a cable C, which is mounted on the cable joint connected at joint D to the wall, and a pin joint at E. The first thing is to solve for all the external forces. The two techniques for sum of equilibrium. The conditions for equilibrium of forces is sum of forces along x equal to 0, sum of forces along y equal to 0, and the moment about a certain joint has to be 0. Now, in order to solve these points and locate these forces, we need to start for the redundant we need to locate the points where we can assume that the structure is redundant. The most easiest way is to start with joint E. With the help of the forces acting at joint moment about joint E, we will be able to calculate the value of T. So, assuming the sum of moment about joint E is equal to 0, we know the tension T is at 90 degrees from the arm DE. As a result, this movement about point E, which is again in clockwise direction, is balanced by two external forces of 20 kN and 30 kN acting at joint C and A respectively. The moment arm of joint C is 5 meters, and of moment arm of the force acting at A is of 10 meters, and we can introduce those values to say that the moment is being rebalanced by these two forces. We can find the value of T, which is 80 kilonewtons. There are two other external forces are acting at joint E, EX and EY. As we know, pin joint will only have two reaction forces, and two-dimensional pin joint will have two reaction forces, that is acting along x-axis and y-axis. So we can start with sum of forces acting along x-axis equal to 0. As a result, we know 80, that is T, cos of 30, this component is balancing EUX. As a result, we have the value of EX acting along x-axis. On the other hand, we have sum of forces along y-axis equal to 0, that is 80 Newton force sine 30. The component of T acting along y-axis is being balanced by EY and two external forces acting at C and A, and from there we can find the value of EY. Now, these forces, this calculation is going to provide us with the external forces acting on the structure. Now we are going to calculate for the internal loading, or the forces acting on the internal members. The best way is to start. Now, once we have determined the external forces, we are going to solve for the internal forces. As we have learned before, that the most basic way to start solving for internal forces, we need to find a joint where there will be only one known, at least one known, and maximum two unknowns. The most suitable joint in this particular example is joint A. Here we have the two unknowns as AB and AC. Now if you look at the legend right here, we know that AB will have, it's difficult to control mouse and use it for pen. Yes. Now the two components, AB will provide the two components, one along y-axis, the other along, other along x-axis. We know the angle between an isosceles triangle is 60 degrees, and we can find that AB along y-axis is going to be a projection of cos of 60, which is right here, which is equal and opposite to a 30 kilonewton force acting at joint A. From here we can find the value of AB. Now, from here we have calculated the value of AB. It is our assumption that it is under tension, as we have started with the basic assumption. Furthermore, we know a projection of AB acting along x-axis is equal and opposite to the force introduced by the element AC, which can be calculated from here, and hence the value of AC can be calculated. Now remember, these tension T and C for compression are assumed initially based on which direction we were able to solve these two unknowns. Since our results are not negative, they are positive. This means our initial assumption for these elements to be in tension and compression respectively are correct. Once we have solved joint A, we are going to move to another joint, that is either B or C. The condition again comes into play that there should be no more than two unknowns. And if you look at joint C, we have more than two unknowns. Number one, the first unknown is BC, the second unknown is CD, and the third unknown is CE. This means there are more than two unknowns. So this is not a good place to start. If you look at joint B, we have two unknowns again, that is BC and BD. So two unknowns are safe. Since as we know, this component AB is known, as we have calculated by solving joint A, we are going to move to joint B now. If we look at joint B, we can apply the condition of equilibrium. Sum of forces along x-axis equal to 0, sum of forces along y equals to 0, and we can find the value of the two unknowns, that is BC and BD. Similarly, moving towards joint C after solving joint B will provide us again the same thing. We have two unknowns, that is CD and CE. Solving again, we can move to joint E afterwards, and in joint E the only unknown will be DE. Now once we have reached joint E, you are going to realize that the sum of forces of this particular joint, the internal forces acting along x-axis and the sum of forces acting along y-axis, should balance the external forces, which is in fact are checked that our calculations are correct. We are going to solve one more example with a different approach. Here in this particular example, we are not provided with internal, or you can say external loading. In fact, we are just given a letter L, and we know that the elements are arc, or they are circular in nature. There are two arcs, that is A, B, C, D, E forming an outer arc, and H, G, F forming an inner arc. The angle between each segment is provided here. As you can see, the angle between the two segments DE, CD, BC and AB of the outer arc is alpha, which is presented here in the problem as 22.5 degrees. But the angle between GF, HG is 2 alpha, that is 45 degrees. In order to solve this thing, we can start from a joint again with one known external loading, and two unknowns. Point E seems to be a perfect candidate. Starting from point E, if we look at this, we can start solving. We know that the two unknowns are DE and FE. Putting them in a free body diagram, and we can solve the sum of forces along y-axis equal to 0, sum of forces along x-axis equal to 0, and from there we can find the value of DE and EF in terms of L. Remember, when you're solving, we have to first assume that our element is in tension or compression. From there we are going to start solving our problem, start going to solve for our structure. Now There is an additional information given here for finding the lambda, and all this strategy is technique is being done to calculate the value of beta, as we don't know exactly at which angle it is going, the direction of the force is. It is a simple trigonometric relation. You can solve it by the help of simple isosceles, you can say equilateral, not equilateral, isosceles triangle. Now once we have solved for joint E, we are going to move to joint F, as again we have two unknowns, that is FG and FD. From joint F we will be going to joint D. Once we have solved for joint F, we are going to go for joint D, and from joint D we are going to find further unknowns, that is CD and DG in term of L. These calculations are similar for all the numericals available at the end of the book, end of the chapter. We are going to solve for, we are going to solve for further numericals. If you have any questions, feel free to contact me. I will upload certain additional numericals for you later on. For this particular chapter, you will be practicing questions from 4.1 to 4.26. I would prefer that you submit me your assignment in terms of PDF file, and you send me a PDF file or zip file with your registration number as your file name. Thank you.